The largest buyer of AI compute just proved it can design a chip that beats its supplier's best hardware at interactivity. By successfully taping out this silicon, OpenAI converts its relationship with Nvidia. What was previously an absolute dependency is now a negotiation. This is Jalapeño. It is OpenAI's first in-house inference ASIC, and researchers from SemiAnalysis have now verified the hardware's performance in the lab. This chart shows the verified headline claim. On DeepSeek R1, Jalapeño processes over 700 tokens per second per user. On Kimi K2.5, the gap widens. At 100 tokens per second, Jalapeño maintains a 9 times performance lead over the next best chip. Unlike startup hardware that etches a single model's weights into metal, Jalapeño remains fully programmable, setting a new ceiling for flexible inference silicon. The compute die is a single reticle-sized piece of silicon, fabricated on TSMC's N3P node. It draws just 700 watts per compute die, a significant reduction compared to the 900 to 1150 watts required by Nvidia's Rubin. To understand the exact mechanisms driving this kind of hardware data the day it drops, make sure you're subscribed. By achieving this level of low-power interactivity on internal silicon, OpenAI is establishing the capability to serve its own models without relying on merchant silicon pricing. OpenAI intentionally built a chip that loses on paper compute. Jalapeño delivers 13.4 petaflops of NXFXP4, trailing the 17.5 petaflops of NVFXP4 promised by Rubin. This scatterplot visualizes the trade-off. Jalapeño sits lower on the raw flops y-axis, but on the GPT OSS model, it is pushed aggressively to the right on the x-axis, driving nearly double the ISO interactivity throughput per megawatt. At a concurrency of 1, its throughput is more than 50 times that of Nvidia's GB200. This dynamic effectively falsifies the FLOPS first mental model of AI inference hardware. Raw operations per second do not dictate the user experience. The mechanism driving this victory relies on a memory bandwidth-led design. Looking at this schematic, you can see the critical specification. Jalapeño surrounds its compute core with HBM4 memory, delivering 15.4 terabytes per second of bandwidth per package. This HBM4 runs at 10 gigabits per second pin speeds, edging out the 9.6 gigabits per second Nvidia achieves on Rubin. This extreme bandwidth directly feeds a weight-stationary MXFP systolic matrix engine, engineered with smaller array shapes to avoid performance cliffs on mismatched matrix dimensions. To manage this data flow, OpenAI placed a contrarian architectural bet. They utilized out-of-order cores paired with a real L1 cache, rejecting the industry-standard software-managed scratchpads entirely. In the interactive serving frontier, memory bandwidths and local caching completely dictate speed, rendering raw flop counts a secondary metric. The current industry standard for handling traffic is prefill-decode disaggregation. This method splits the processing pipeline, assigning the initial reading of a prompt and the subsequent generation of text to entirely different specialized pools of chips. OpenAI completely rejected this orthodoxy. Their rationale is that real-world workload ratios drift continuously throughout the day depending on user behavior. When ratios shift, disaggregated fleets strand massive amounts of fixed chips, forcing them to sit dark while queues build. It also breaks cache locality by forcing massive network transfers. OpenAI solved this by keeping the entire process on a unified loop. Jalapeño achieves this unified design by dividing its high-bandwidth memory into low-latency local views, specifically mapped to each individual core slice. Synchronization between these slices is handled by a dedicated high-bandwidth collective network that manages tensor parallel communication seamlessly. Prioritizing raw hardware utilization and keeping memory access completely local creates a highly resilient fleet, capable of absorbing unpredictable, multi-turn agentic traffic. The speed of this bring-up indicates that the software barrier, often cited as the primary defense for the CUDA ecosystem, can be bridged much faster than previously assumed. OpenAI programmed the chip using their internal glue-on stack. It relies on an abstraction called linear layouts, which provides a mathematical framework for provably correct layout conversions. To actually write the code, OpenAI deployed their internal Codex model, which produced sprawling 3,000-line kernels from scratch. These blocks of code included complex multi-head latent attention kernels, generated entirely without intervention from OpenAI's human kernel engineering team. Shifting to physical deployment, the reality of running the software requires massive scale. A deployed system pairs an AMD host CPU rack with custom ASIC racks to form a massive compute block. These blocks scale aggressively, connecting 2,048 Jalapeño XPUs within a single scale-up network across 16 racks. Looking at this thermal render, you can see the environmental constraint. The power draw for this combined dual-rack setup sits at roughly 160 kilowatts total. A 160 kilowatt profile is far too dense for standard commercial colocation contracts. This hardware will stay exclusively on the hyperscaler side. External builders will never buy Jalapeño directly. The market will only experience its compute power indirectly through the reduced latency of OpenAI's API. When comparing Jalapeño against Nvidia's Rubin on total cost of ownership, the two chips are currently head-to-head on the number of output tokens produced per dollar, but there is significant economic headroom. Rubin's total cost of ownership relied on speculative decoding to achieve a 3 to 5 times cost reduction. Jalapeño achieved parity without even turning that software lever on, suggesting immense unrealized margin. We have to analyze the boundaries of this data. Every benchmark verified by SemiAnalysis ran on OpenAI's own hardware, utilizing OpenAI's specific configurations. This chart restricts the view to the exact parameters tested. The workloads shown to the lab were limited to a highly curated 8,000 input, 1,000 output inference-X slice. This specific testing regime inherently flatters Jalapeño. It avoids the memory-devouring complexity of massive, long context windows, allowing the chip's raw local bandwidth to shine without stress testing its caching limits. Critical data is entirely missing. There are no multi-turn, long-context AgentX benchmark results published. Furthermore, tested models like DeepSeek R1 sit below the open frontier, whereas Nvidia tests much larger models. There's also an asynchronous timeline. Tests ran on an A0 engineering stepping. Actual manufacturing volume won't ramp until late 2027. By the time Jalapeño hits volume production, it will not be competing against the Vera Rubin chips shipping today. It will face whatever architecture Nvidia decides to ship next. The industry has two tells to watch for. First, whether OpenAI publishes those multi-turn AgentX numbers. Second, whether their purchasing volume of Nvidia hardware flattens out through 2027. Jalapeño proves that OpenAI possesses the silicon architecture and the software velocity required to challenge the CUDA moat. But true victory depends entirely on this chip surviving contact with real, unpredictable agentic workloads in 2027.